So good morning, welcome to day 2. We are packed on the agenda in the morning. Very interesting actually for those of you who like to understand where architectures are going. This is going to be a good morning for you, so we'll have a session really just starting to think about what do we mean by flexible infrastructure. What are some of the concepts around that and how architectures are going to evolve as we start looking at different deployments and needs going forward around chipsets and products. And no conference these days is complete without the mention of Open RAN, so we must make sure that we think about the implications of Open RAN on the small cell ecosystem, and that's going to be covered again. Today was mentioned, Open RAN was mentioned a couple of times yesterday, and it will certainly be given a good looking at in the morning today. So that will take us through to lunchtime. In parallel to that, there will be, some of you have been, I'm just going to take the opportunity on stage here to say some of you have been invited to round tables to have a discussion with DIT, DCMS, UK government representatives here to talk about private networks. So if you've received an email for an invite, please do remember there's one round table at 11 and one at 12. So if you've received those mails, please make sure that you turn up. If you go to the reception desk, they'll point you to the meeting room, which is upstairs. And those round table discussions will help to seed some thoughts about a program of activity that we'll run over the next year, focusing on the private network ecosystem and how that's going to develop. And we'll certainly be talking about private networks next year. That'll be an important central pillar of what we look at next year's Small Cell World Summit. But this year we'll have after the conference has formally closed at lunchtime, we will have then in the afternoon a private networks workshop, which you're all more than welcome to. I know that's again also a very interesting agenda. I shall be chairing all of that and orchestrating this afternoon, so I hope to see all of you for that. Right, so now we're going to go into this morning's session, as I say, very much focused on architectural discussions and the trends and the commercial issues around some of the architectures that are emerging. And a friend of the forum who's, I think, not been to the Small Cell Forum for a while, but many of you will know Doug very well in terms of his capabilities to develop chips. He's a good, very, very capable chap on that. And Doug's going to give us some thoughts in terms of how architectural diversity can be managed in the constructs of a small cell ecosystem. So Doug, can I invite you to the stage, please, to give us our first keynote. Thank you.
Thanks. Thank you, Simon. So, do we have it on? Right, we're going. So, enabling architectural diversity. So normally when somebody talks about diversity with regard of the RAN these days, what they're really going to talk to you about is supply chain diversity. For a long time, from the beginning in fact, the average radio access network was provided by, say, a couple of vendors in a particular network. Those vendors would each provide their end-to-end solution for all their pieces of the RAN, and they really, and they were completely indivisible lumps. They were completely monolithic, and the piece of RAN from vendor A wouldn't talk to the piece from vendor B, et cetera, et cetera. And it's really been like that, largely speaking, like forever. And obviously, the move to disaggregated RAN and movements like Open RAN are really trying to move towards a world where you can select from best-in-class of the various pieces of equipment for a radio access network, be they radio units, distributed units, centralized units, to name a few, and thus end up with a picture a bit like the the right-hand side of this particular slide. But I'm not going to talk about supply chain diversity. I'm going to look at the diversity of the challenges of the real world to act as a reminder of the problems we're trying to solve. And in the time-honored fashion, to actually, in order to look forward, to look back at historical trends, to try and figure out how we got to where we are we now, and where do we need to go. So, in the beginning, the world was very simple. The world had one of each of the major things you might care about. There was one frequency band, typically sort of around about 900 megahertz. There was one channel bandwidth, say 25 kilohertz. There was one standard, although that standard might be different depending on which country you were residing in. Typically one sort of cell or cell equipment, sort of a macro cell type of thing. And one well-understood traffic type, circuit-switched voice. So that was a very well-ordered, apart from the L in macrocell, a very well-ordered and low-entropy environment. Nice and simple and straightforward, so you can concentrate on all the other problems you had to solve. But the last 3-4 decades have seen this happen. So this big bang on many dimensions has made the world far higher entropy. You've now got plenty of frequency bands to choose from over a very wide range of spectrum. And actually within each of those frequency bands, you've got different channel bandwidths, and you can combine them in unimaginable permutations. There are new tools in terms of air interfaces, ever more intricate to try and deliver services to users. It started analog and they've all been digital after that. And the traffic, the problem that you're trying to solve, the services you need to deploy are now not just circuit switch voice. Circuit switch voice then became circuit switch voice plus packet switch voice and data and text and video, etc., etc., etc. So that's another dimension. And to try and figure out how to map all this to the environment, we've gone from sort of one-size-fits-all RAN base stations through to ever smaller and more diverse pieces of equipment. And all that is to try and get best user experience wherever they are, down into every last nook and cranny of the environment. Since the beginning, people working in wireless have angsted over the dense urban environment because it's difficult from an RF standpoint. It's difficult because there's loads of users. That tends to go together, high subscriber density and difficult to reach RF areas. But this is not the only environment. There's lots of different environments. And to reach into all these areas, you need a much more flexible strategy. So in the beginning, there were some vague attempts to try and accommodate the real world. Whilst I said that there was one of all of these resources and problems to solve, there were actually two different types of diversity out in the environment. There was the user density, how many users per square kilometer there were, and the environment in which they lived. And you had 2 degrees of freedom to try and map your network to those diverse challenges. You had cell radius. You could make the cells smaller. As you can see on this diagram, from the rural areas where there's a sparse scattering of users to dense urban where there's a lot of people per square kilometer. And you could add extra capacity to those cells. You could add extra channels if your cell planning rules would allow it. And these are all facets of all the drivers behind a thing called Cooper's Law that some of you may know. Cooper's Law is a sort of really a characterization of exponential growth in the number of wireless connections around the world over time. And the primary drivers of increasing those numbers of connections have been reducing the cell size, adding more spectrum. So that was all very well. And then the traffic came. So originally, certainly in the UK, the sorts of people who had mobile phones were tradespeople, they were business people, they were people who had an absolute driving urge to have a connection wherever they were and to be able to be contacted because it was expensive. And then, you may remember, pay-as-you-go was invented. And suddenly it was affordable and accessible to the general public. And so there was a lot more traffic. And so the first port of call was more Cooper's law. You could split the cells down using sectorization. You could start to add new cells, microcells being things you site below the rooftop to try and tailor the coverage, to try and add capacity into those, and coverage into those difficult to reach areas where people were annoyingly having to go. So much more attention was then paid to mapping your network to the environment. And then the real change was phones got the internet and fitted in your pocket. So people tended to hang out more indoors. It's warm and dry indoors. And there were various stats quoted yesterday about the huge percentage of traffic. The vast majority of traffic is generated indoors, be it in residential settings, in office, business settings. But there's a huge but with all of that, because information doesn't pass through walls quickly. See Claude Shannon. Well, he didn't actually say that exact sentence, but it's a logical deduction from things that he did say. But the world's more complicated than just residences and offices. The world has all these different facets, each characterized by, each scenario is characterized by a user density and RF challenges. Stadium is the sort of, I guess, the optimum of the density problem that you need to solve. Lots of people in a very confined space, all wanting to, play back video replays of the goal they just missed. Because they were queuing for a hot dog, whatever, or a pie, probably more likely in the UK. And then you've got the outdoor, you've got the enterprise of dense urbans. They're all characterized by different radio environments, different subscriber densities, and different ability to actually physically deploy equipment. So that's a nice marketing slide that shows you, all these sort of interesting different environments that one could imagine. But they do really exist, and they exist in close proximity to each other. So this is a satellite photo from Google Earth of Bristol. You can see a logo just off the middle there, which is where Picocom's Bristol offices are. But you can also quickly see there's dense urban, there's suburban areas, there's a stadium, there's a shopping mall. My daughter knows it far too well. And mass transport, Bristol Temple Meads. And if you look at the scale on the bottom of this picture, you can see how big 400 meters is. So these things are all packed together in quite a small area in real terms, and they're all got very different challenges. And the trouble is those challenges are not static. We're in a world where there's already, and people might be familiar with this triangle diagram originally from ITU of the three different forms of traffic envisaged. You've got enhanced mobile broadband, that's more of what we're already used to. Then there's the ultra-reliable and low-latency comms and massive machine-type comms. So there's already a plan for a very diverse range of traffic, and it's not staying still. 3GPP are busy on reduced capacity specs for UEs. Extended reality and metaverse is much talked about, and there's even discussion of the use of holograms over 5G. So it's not going to get any better. But fortunately, there's more resources coming along. Frequency range 1, we're all familiar. Those are the usual frequency bands that we've been familiar with in more recent times. Millimeter wave, FR2, is going to add much more spectrum, and then terahertz, an awful lot more spectrum in order to deliver services. but each of them has their own sort of superpower. You can either have lots of bandwidth, or you can reach indoors from a long way away, but you can't have both at the same time in the same band. They're rather mutually exclusive, typically. There's new tools. I mean, 3GPP does not sleep. So we're all familiar with 5G. 5G Advanced has just kicked off, and 6G is also one of those things that's filling the conference diaries at the moment, and will continue to do so. But those are standards, new ways of tools to reach people. But there's also new technologies in conjunction with that. Machine learning is alive and well in things like radio intelligent controllers, RAN intelligent controllers. But 5G Advanced includes study items on use of AI in the air interface, AI in the AI. And who knows where that will lead to. But all these are new ways to try and manage complexity that has arisen in the last decades. And architectural diversity, if we chop things up right, can do all sorts of new things as well, though. You know, if you're in the cellular game and you worry about air interfaces, you know that the barriers to delivering vast amounts of bits per second per hertz per square kilometer are all about making sure you don't have too low a signal relative to the to noise interference, that you mitigate against obstructions, slow fading, shadow fading, and that you mitigate against distortions such as dispersion, multipath between you and the antennas. You can mitigate this by surrounding, in the limit, you can mitigate this by surrounding users with lots of antennas, at lots of different angles of arrival to where you are, scattered around the service area. You can process them jointly. If you've chopped up where you put your radios, where you put the combining distributed units, and how you manage that in the algorithms used, you can have distributed massive MIMO. Lots of extra capacity in all the right places. So we say architectural diversity. So how are we going to do that? So we talked about RUs, DUs, and CUs up the front. They're not, fixed definitions. There are fixed definitions, but they're variable. There's various choices that you can make. The important bit is putting the radio units where they need to be for the users. That's what wireless is all about. That is what's necessary. But you may have different abilities to route signals back from where you put radio and as antennas to further processing down for the rest of the network. There may be limits of latency and bandwidth and availability and et cetera, of what you can do to route back to the network. So you have choices, different splits available of how much processing is in the radio units, how much is in the DU, in order to pick the one that suits your particular environment. But diversity doesn't stop in just the environment. There's diversity in the actual signal processing itself to enable things like I just showed you on the previous slide. So ultimately, there is a variety of things that you need to put on silicon in those boxes in order to make them work. And a PHY is made up of many pieces. You have pieces that are more naturally suited to software, things that should live in general purpose processing cores like APIs and PHY control. You have things that should live in digital signal processor cores, which is your general signal processing, obviously. But then there's things like high-performance equalization and other specialist signal processing things that maybe need a bit of hardware acceleration. There are things like particularly channel decoders, which have been a thorn in the side of chip designers since the beginning of 2G, which are very high-performance requirements from a mass standpoint and throughput standpoint, which are best off in dedicated hardware. And then there's interfaces and flexibly interfacing to lots of potential radio front ends that you might need to do. So you need to choose a mix of all these things to create a sort of a system on chip that can enables the flexibility to build all those boxes that we talked about, but has decent cost and power characteristics. So if you do that right, if you've chosen the right blend between very hardened and very software, somewhere at a careful choice in between, with the right interfacing, you can enable one chip, different software builds for the community of new OEMs that are rising to meet the challenges of disaggregated RAN, to produce many different flavors of boxes that have different antenna combinations, different bandwidth combinations, different standards, different splits, using and really gain out of the usual economies of scale and semiconductor economics. So, in summary, we have a lot of services now, many of which haven't all been fully deployed yet. We have new services coming along. They need to be delivered. We have new resources coming along to allow them to be delivered, and that's not standing still, and neither is 3GPP. So there's new standards, and there's new tools, new engineering technologies like machine learning to help that happen. There is architectures which you need to be able to build to embody those standards and those tools, to use those resources to deliver those services to very difficult environments. And it isn't just one environment, it's lots of environments. And with that, I'll leave you.
Okay, thank you, Doug. I'm just going to ask one question. I'll look for hands. We only have 2 minutes, so I won't hold you long, Doug. But I'm just interested.
I should have spoken for longer.
Yeah, I don't want to. I'm interested in your diagram. You talked about the different splits, and you had two in the diagram. You selected 2, 6, 7, and 8 as the splits.
7.2 and 7.x.
Yeah. So what? In terms of thinking about how those splits are going to evolve, now clearly in your architecting, you've decided that you can support all of those different splits within the same silicon.
Yep.
And how's that going to play out in terms of, there's a debate about, do the splits really matter in terms of, can they just be reconfigured in some clever software way? And it sounds like actually you can, I'm guessing there's going to be a degree of, once the architecture is deployed, then the interface is defined, but in theory it could be re-architected in situ?
I think the point is you've wired it to some front hall, you've got a particular access point you've put out there, unless you're going to churn that on a very regular basis, you're not going to be changing anything. So typically that's not really perceived as a thing that's going to happen.
Okay, so you wouldn't envisage a use case or the network's been deployed and then for whatever reason you decide to reconfigure at that sort of low-level functionality, the interfaces, you think that would be decided at deployment time? No,
because I think you'll have engineered that to the environment you've got, whether it's an office block and whether it's a resident, whether it's a shopping mall, and you'll have engineered that because that's the radio environment you've got to deal with and the sorts of traffic capacities you've got to deal with. Maybe where maybe more interesting reconfiguration on a much more regular basis is actually higher up in the stack.
Right.
The higher layers of DUs and CUs.
Yep.
Where as sort of traffic might evolve through a day or through a week or over.
Got you.
Over time.
Okay. All right. Thank you. Any questions? Oh, there's one there. We'll just take one, and then we'll move on to the next session. Just the hand there.
Andy Jones the Phone Consulting. I think it's been really clear that ORAN wanted to intercept the rollout of 5G, but everyone will have their own opinion on whether actual deployments will need to have LTE support. So what's Picocom's view on that, and is that built into your products and your solution today?
Yeah, so the devices will have been designed specifically to support 4G and 5G. You know, I think legacy is the bane of the cellular world. Handsets and technologies hang around for a lot longer than you ever expect. You know, there's plenty of 2G still out there. So yes, those sorts of things are definitely factored in.
Excellent, thank you. Thank you, Doug.
Thanks.
Right, now we're on to our next session, and this will be chaired by a familiar face to many people in this audience, in this forum. So I'd like to hand off now to Simon Saunders, who's going to take us through Architectural Evolutions section. Thank you.
Brilliant. Thank you very much indeed, Simon, and good morning, everybody. So yeah, I chaired the first of these conferences 15 years ago, and it's been a few years since I came to one, so it's really great to see actually some familiar themes being explored in greater depth and some new themes as well, and to see so many people with an interest in small cells. So I'm very happy to be here and to chair this panel. And let me tell you a little bit about how we plan to run it. So I'm going to give some opening comments, very much building on what Doug has been setting out, which is very much the landscape of this discussion around architectures. Then I'm going to invite our series of panelists to each give a 15-minute set of views on their own thoughts on these architecture evolutions. And we've got a really great panel with actually 3 companies representing the semiconductor landscape, one you know, as an OEM, and one really actually putting these things into practice in buildings and so on. So I think we can have a very well-rounded discussion and debate around these things. With each of the presentations, if you have questions directly about their presentations for clarification, happy to take those at the end of each of those presentations, but I'm going to really keep the time limited, and I'd ask the speakers to respect that so that we can really open up for a full panel discussion afterwards. So, you know, hold your more probing questions, if you would, until the end, and you'll get your chance to ask them then. So, indeed, we're really exploring architectures, and Doug set out that there is a very wide range of choices available to us. You know, from the days when we had macrocells, and then occasionally, if we wanted to serve a big place like an airport, we'd plug some of those macrocells into a distributed antenna system. Suddenly, we've got this huge range of new choices. And Doug set out many of those. We have the different splits in the Open RAN. We have different ways of implementing our systems with probably more software than we had previously, but equally, we're seeing a lot of new devices and materials used to actually make the radio end of the systems, particularly as we go up to the FR2, the millimeter wave and beyond, to make those efficient. We have the whole gamut of small cell species, of course, from outdoors to indoors, from pico to micro to femto, to choose from. We have sort of physical questions, though. It's not just architecture or perhaps marketecture diagrams. It's also where do you actually physically locate your DUs and your RUs and your CUs, respect to the users for the radio reasons that Doug mentioned, and with respect to where you want to aggregate systems together, with a great dependency, of course, on your front haul, your mid haul, your back haul capabilities in place. And then you've got this sort of stack of spectrum options. And again, it used to be that, for example, for in-building, there was really just sort of one channel in one frequency band. But indoor users should expect the high end of the data rate and the latency experience. And therefore, you know, you've really got to aggregate carriers across multiple components, multiple spectrum bands. So how does that play out and integrate with the macrocell environment? You've then got sort of a different set of users, not only doing different things from you know, video to various sorts of data. I was at an academic presentation yesterday about the Internet of Smells, so that's coming to a building near you very soon. But you know, as well as those services, you've also got a different set of usage models, from you know, a mobile operator-driven deployment through to a multi-operator one, through to a private deployment, perhaps in shared and local spectrum, and neutral hosts making that work together on a multi-operator basis at various levels. Now, you could see this as a problem, and I think it's quite common that in the press they want to paint some kind of war between these architectural options that are there. But I think positively speaking, it means we've got more tools in the toolkit as engineers to tailor these systems to meet the very wide range of radio environments that Doug was showing. And I think there's really no reason if you stand up on a rooftop in the middle of a busy city and look out and try and cluster the buildings that you see into standard categories, it's a very, very difficult job. And to have efficient radio solutions, we need almost as many types of architecture and of system to properly tailor the coverage, the capacity, the user experience into those places. So what I hope from this panel session is that we emerge not with a view as to which is the one architecture to rule them all, but rather of the pros and cons of the different architectures, and perhaps edge our way towards a little bit of a designer's guide, as it were, for which of those colours of paint to reach for in the paint box as we go. And I would say, talking about boxes, it's not only at the level of full equipment, but clearly, and we'll explore this here, it's what's inside the box as well, as we realise that virtualization doesn't mean putting everything on completely generic off-the-shelf servers, but we have lots of questions as to the CPU architecture, the accelerator architecture, whether we need very customized silicon, or whether borrowing specialist chips from the world of GPUs, for example, might help us. So many things to consider, and we'll come back to those. I hope that gives a sense of the landscape we're going to explore. I'm going to start by introducing the first of our speakers, Andrei Radulescu from Qualcomm. Andrei, please.
Okay. Thank you for the introduction. So I'm Andrei Radulescu from Qualcomm. And I will be presenting today the architectural evolution for cells of various sizes, as well as deployment of various types and use cases of various needs. So let's get started. Okay. So let's take a brief trip down memory lane. Way back when we talked about our base station, it would be a set of components, a baseband unit, and a radio unit located at the cell tower, at the cell site. And somewhere towards the middle of the LTE deployments, the baseband unit migrated towards the centralized location in order to benefit from various trunking, basically trunking opportunities. And the fiber, typical fiber that would connect the baseband unit to the radio unit would carry the IQ samples. And then more recently, we have this yet additional disaggregation that happens, where the baseband unit now is not just the baseband unit, but it's split into the CU and the DU, where the CU is definitely centralized, and the RU radio unit is going to be at the cell site. And then DU is going to be somewhere in between, depending on the needs of the deployment and of the operator. So this sort of these three components together, you can sort of combine them like Lego blocks in multiple ways. You end up with a very modularized RAN, which addresses various needs. So for instance, let's focus a little bit on this DU. So this DU now can accumulate multiple cell sites. And then as a consequence, it can enable various high-performance use cases. You could have a situation where you have a joint MAC scheduler residing in a DU, or, and that would allow you to enable advanced features. In release 15, for instance, the GPP introduced this MTRP architecture so that the centralized DU would easily enable that. Then you have these various nodes, the DU itself, which collects a lot of samples, but also the RU and the CU, that now if you are able to combine them and then present them to a data analytics function, then with a Lego-like deployment, as long as the data analytic function is also open, you can end up optimizing the network for various needs. Now, for instance, you could have a situation where you're deploying a network and you know the coverage that you want, but you don't know necessarily how much capacity you want. So you can start with the DU, set of DUs, and with a bunch of accelerator cards that would address the basic need. And then if you see that the need increases, you add more cards. So you can easily scale with this architecture. Another use case is where you have kind of a heterogeneous network. So you can have your typical wide area network, in which case you would benefit from the 3 nodes, the CU being kind of like a national level or kind of more centralized, the DU needing more beefing up to process all the physical layer functions. It would be kind of more regional. And then the RU being a little bit of a smaller box. Now you want it up the cell site. It's a smaller footprint. You don't really want to touch it that often. And you can, whenever you need to play with your deployment, you'd be touching more the DU and the CU components that are easier now to reach. And another use case is private networks, for instance, where maybe the need to have DU and CU separated is lesser. So then you can combine them, and then you end up with a two-box solution. And now you can see sort of that you have a trade-off that you can establish to target a particular deployment, and you can target for performance, you can target for flexibility, you can target for price, and this is all arising out of this modularized architecture that you can combine like Lego blocks to establish whatever need and coverage that you want. So let's take a little bit of a deeper, but not too deep look. On this architecture diagram, you have on the left side, you have the core network, and on the right side, you have your access network. Now, an access network would have multiple protocol levels, layers. So on top of RF, you have PHY, which can be split into low-PHY and high-PHY. You have a MAC, and then RLC, PDCP, RRC, and then SDAP. All of this SDAP was added in 5G. And originally, these layers were, while they're so logically separated, they were sort of meant to run in the same box. And with the LTE deployment maturing and then trying to target multiple use cases, and then 3GPP evolving into 5G, they realized that sort of this single box approach doesn't work. So then they looked at how to split these various protocol levels. So essentially, one box, one size, one solution does not address all. So then you ended up effectively with various splits. So back at the beginning of 5G, 3GPP ended up with this effort of looking at the various splits of protocols, and then they decided to focus more on option 2, split 2, which you can see here. It separates PDCP from RLC, and leave other splits for other groups to develop. So 3GPP effectively has this F1 interface that addresses option 2, and then the option 6, which separates MAC from PHY, was developed by the Small Cell Forum and continues to be developed by the Small Cell Forum. And then option 7.2, which effectively has this front hole that runs a control user and the synchronization plane. That's being developed by ORAN. And the openness of this interface is crucial, because if you think back to Lego blocks, right? The Lego blocks have to fit into each other. If you don't have an open interface, you can't fit them, and then you don't really have a solution that is sort of modularized. So it's really important to have this openness. And you can see here that with these solutions, then you can build single box solutions, such as basically distributed small cells. You can build two-box solutions where you can decide whether you really want an option 2 split or you want an option 6, option 7 split. And those are available depending on, for instance, if a distributed small cell enterprise, that's one option. Or you can have standalone cells, option 2. So it enables all these options. And obviously also the option 7.2, if you choose it, then you can have an RU and then a combined CU GU that we discussed in the beginning. And obviously the 3-box solution is also possible part of this, which splits CU and DU. So right, so part of this box, basically part of this disaggregation, ORAN in particular, added one more node, or added multiple nodes, but one more node I want to focus on, which is the RAN intelligent controller. So you have these RAN boxes that we just discussed. The question becomes, how do you configure them? How do you automate them in a way that doesn't sort of complicate life? And you'd want an open interface, and you want to be able to deploy optimization functions in a way that is supported in a multi-vendor fashion. And this open interface effectively would be connected to the RAN intelligent controller that would be able to sort of extract KPIs from RIC, from CU and from DU, and run functions either on a kind of a long-term basis, like talking about seconds or hundreds of milliseconds a second, called near-time RIC. You'd end up being able to optimize the network as needed. And again, the openness of these interfaces allow the optimization to run in a consistent fashion. Now, let's go back to the DU and focus a bit more inside the DU. So here you have a DU, that kind of the big rectangle, with two options for acceleration that the ORAN has defined. So one option for acceleration on the top is that the MAC function interacts with an application layer that implements, that essentially takes the functions that would benefit from acceleration, implements them in this look-aside fashion, and then extracts the IQ samples and sends them, or the other way around, it receives them and drives them to these accelerated functions. And then on the bottom, you have this alternative that has the accelerator interacting directly with the application in the MAC, where the transfer blocks are shipped to the application, are shipped to the acceleration. The acceleration is very narrowly tailed to the needs of basically to the particular 5G functions that are very well understood and very well known. And then you can ship IQ samples on the other side and then process them to the accelerator and then make them available to the Mac application on the uplink. So you can see here that rather than implementing these 5 functions on CUTs, you can implement them in a much more efficient way in these application-specific hardware functions. And with that application, you can focus your energy on addressing those rather than wasting it on various other unnecessary processes or wasting it in ways that do not properly address the channel processing needs. So then you can have essentially a reduction in size and a reduction in power. And as a consequence, that also leads to a reduction in weight. So now you're in a single DU block. Now you can address, not only do you basically you have this more efficient functions, but you can scale more easily. So rather than adding a few more kind of slab cards, you're going to add a few more PCIe cards inside the slab, and then that will be able to allow you to scale better. So we talked about scaling, right? So that's one. this DU and CU, a separate node from the RU. They allow you to target your function to scale as needed. So for instance, as I mentioned, you might deploy initially, you don't know what your requirements are. You'd be able to have a virtualized function, and you can dimension that virtualized function. You don't have to have that virtualized function run on a dedicated cloud or the dedicated hyperscaler only for that function. So you can host other functions. Here you can host the edge compute function. You can also host other functions that are specific to the use case. So you have the secure maybe data process user plane function hosted in one container, and then maybe the public user function hosted in another container. Okay, let's skip a little bit just to make sure that. So focusing a little bit more on the Small Cell Forum, which graciously organized this conference, the split 6, effectively, it's not just it's not the only focus of the Small Cell Forum. Effectively, the work of the Small Cell Forum enables all the other splits. By having this FAPI function that separates what's naturally software functions of the Mac from the hardware functions of the physical layer, then you have this crucial interface, FAPI, that connects the two in a way that makes it possible to further modularize the architecture. So it enables pretty much all the individual RAN architectures by placing these FAPI functions appropriately inside a single node, inside the DU, or inside the combined CU and DU, or on a network interface that separates the DU and the SDU and SRU functions. And yeah, of course, this leads to innovation. This leads to acceleration of the feature development, because then you can have multiple vendors competing and resulting essentially in them trying to optimize these networks. So all this enables a modern network, which consists of your regular public networks, but now you can have massive MIMO, which is supported across all these interfaces. You are not limited to public networks. You can have them you can have private networks. You can deploy massive IoT. If you need fixed wireless access, then that's also enabled by these interfaces. URLC is another function that is also that you can target this RAN disaggregation functions towards. And of course, I would not be remiss not to highlight that Qualcomm participates in a lot of these nodes where we're not an infrastructure vendor, and there are a lot of companies that do a very good job at that. Our specialty is essentially modems and RF. So we will be focusing on enabling the modem and RF solutions and making them available to infrastructure vendors to integrate in the solutions. And for instance, we have FSM solutions which are to be integrated in very low power nodes that you can run purely off Ethernet, or you can have this card that would be able to be tuned towards running massive MIMO solutions, or to run your macro solutions. And all of this benefit from these interfaces that I just talked about that allow this modularization and Lego-like fit of RAN disaggregated nodes, CU, DU, RU. And obviously we have pretty much in all those three nodes you have solutions, and of solutions even beyond those, but limited time, and we're just going to focus on that. Thank you.
If you hold on for a moment, Andrei, there might be a question or two for you, just in clarification. Perhaps there isn't. I see now, in fact. So
should I
carry on. Thank you very much indeed.
I'll come back for the panel.
Yes. Good. Okay, so we're moving on to a world of the actual infrastructure vendors now, and I'm pleased to introduce Abel from Airspan. Welcome. Let's give him a round of applause.
Hi, Simon. Hello, everyone. Good morning. Let me start with thanking Small Cell Forum for this event. We have been part of a Small Cell Forum for many, many years. We have been honored to win an award for 4 years in a row. Last night was a special night for us. We won 3 awards, one with Rakuten for Open RAN commercial network, mobile network, one with our starter kit, like pre-integrated Open RAN starter kit for private networks together with our partner Druid. And the third one with a system integrator in the US, Picocom, who is doing 5G as a service together with Druid. So, and I'm highlighting these 3 awards because there are 3 different architectures inside of these networks that goes very nicely with this talk. I'm Abel Mayal. I'm the Senior Vice President of Technology and Marketing at Airspan. Airspan, you might know, is an American company which provides disruptive 5G end-to-end RAN solutions. When I mean end-to-end, we do the software, so the CU, the DU, but we also do the hardware. This is quite unique. When you look Open RAN vendors, normally they focus more on the software side. We see value still on the radio side nowadays, so we do our own radios. Our goal is to disrupt the status quo of how networks are being traditionally deployed. We normally try to do that by bringing simplicity on deployment. So we try to be as much as plug and play as possible. This is one of our key of success. Although we're an American company, we have a very strong presence in the UK. We have an office in Slough with 100 people, most of them in R&D. So today I'm going to talk, and it was very good, the previous talk with Andrei, because it gave me a lot of background that I'm going to explain. But I'm going to focus more about the lessons learned about the architecture. I think it was Simons and Doug was talking about the different splits. What I'm trying here to clarify is the pros and cons, what we have seen, and what is if there exists like a silver bullet solution of a split, or is better to be flexible on the splits, and which use cases, for example, you can use each of the splits. So let's start with it. Just a short introduction. I think most of you are quite familiar with that. And this is like we have like 3 blocks. This is where you position your infrastructure, right? On the right, you have the main building, the headquarters. Then in the middle, you have the edge side, the mobile edge computing, the MEC, right? That could be a cabinet, could be another building. This is normally close to the site. And then you have the cell site, right, where you put the radios. So normally, traditional networks, how deployed, you have a baseband unit that is close to the radio. Normally, this is proprietary software, proprietary hardware, right? They use this interface, CPRI, that is quite resources demand. And the only issue we see is that this is closed, right? So if you buy this solution, you can only interact with this specific vendor. So then it came the operators like a few years back saying, well, we have to open the supply chain diversity. There is not many vendors in this market, so they become with the idea of Open RAN. There is a lot of definitions about Open RAN. Basically, it's virtualizing the radio, right, and using open standards. So now what Open RAN does is that you have the radio on the side, but you're moving the software away from the radio, right? So radios, as Andrei was explaining very well, you have 3 layers, layer 3, 2, 1. So you move them into the DU, distributed unit, that has the lower parts of the radio. And then you have the high part, the CU, that you can put it, for example, in the headquarters. And then it comes this flexibility, the centralization of the software. Having centralized software is very good because then you have visibility of all the radios and you can start doing nice features between them because you know what all the radios are doing, right? The important thing when you start virtualizing is that you have new interfaces. And you can see the F1, the front hall. And here you need to have some standard organizations that defines the standards, how to interact, right, in order to create this multi-vendor type of networks. And we have 3 main organizations that defines the 3, they call it the splits, right? We have the 3GPP that defines the split 2. Then we have the most famous one nowadays, that is the Oran Alliance, the split 7.2. That cuts the physical layer. And then we have another one that is a small cell from that is a split 6. They are important to have these standards, as I said. I think that the 3 has been a lot of studies about which split. I mean, 3 years ago, like which split was the most beneficial. I think that 3 is enough. We don't need to have more splits. I think with this, we cover a majority of the use cases. What I'm going to explain now is like which split we should use, right? If there is one, if there is 2 or 3, that we can combine them and use this modularized radio that Andrei was mentioning. Let's start with the pros and cons, looking at the features, right? It's important when you start deploying a network and you want to know how much, let me see the time. Okay. So it's important to understand what can I support if I use one of these splits, right? So I put here a series of features. I reckon you recognize most of them: carrier aggregation, dual connectivity, beamforming, right, when you start having multiple antennas, multi-user MIMO, to use like different beams to access, to give the whole capacity to different users. And then it comes all these COM, coordination multipoint, in order to interact downlink and uplink and avoid interference, for example. So when you look at this table, we put the 3 different splits and which feature can you support with them, right? Of course, if you look at this table, everyone will say, well, I'm going for a split 7.2, right? I got all the benefits of all the features. And that's great, but there is no free lunch. You also have to look what is happening on the other side that is normally the interfaces, right? So when we look at the splits, but at the level of these interfaces, this F1 front haul that we have, we did here a simple study of what happens if you have a cell, a radio, transmitting 2.4 gigabits per second. You have the data there. So that means that you have a radio and you have several users, and this cell is transmitted at 2.4 gigabits per second. How is it going to be translate this cell throughput into my interfaces, right? So we put 2 metrics here. One is the throughput, the one on the right, the bandwidth. The one on the left is the latency, the delay. So if you see the more you virtualize, so that means the more software you move away from the radio, that would be a split 7.2 ORAN, what you see is that the throughput multiplies nearly for 4. So you get like 9 gigabits per second. This is using a compression floating point, right? If you don't use compression in this front haul, you can get to 10 or 20 times more, right? The other metric, that is the latency, if you see when you virtualize the network, when you put most of the software in a virtual platform, what you see is that also the latencies that you require are more stringent. And if you see, we need less than 200 microseconds. What does it mean? That when you have to deploy a split 7.2, the majority of the cases, you're going to need to have optical fiber, right? What happens with the other type of splits, a split 6 or split 2? If you see, when you keep some of the software on the radio and then you virtualize the rest of the software, you can see that the transport starts to be more flexible. So you can see that, for example, on the throughput side, split 6 and split 2, they're very similar. It's only a 10% more of what you need on the actual radio interface, right? So if you see, it's like 2.6 gigabits per second. But most importantly, the throughput. If you see, the throughput gets much more relaxed. And the throughput is very interesting when you start virtualizing, because the throughput also gets it's very aligned with the distance, right, that you can deploy. So if you think about this CU in the headquarters, a mobile edge computing where you put the DU, and then you have the radios. Now these radios can be maybe kilometers away from this mobile edge computing, from this edge location. So that means that you can aggregate much more radios using the split 6.2. But this is something that you have to think of as some economical advantage as well. So when you start deploying, I think it's good to have in mind which features are going to use. For example, when you go to a macro deployment, it's very interesting to have, for example, multi-user MIMO, because you have a lot of antennas. Normally you have like 32 by 32 or 64 by 64. So multi-user MIMO is going to be needed. And then you want to extend the coverage as much as possible, right? So all this coordination multipoint downlink, but even more important, uplink is going to be critical. So you will see that macros, when you do Open Run, they use Open Run, they use a split 7.2. They use a split 6 or split 2. So I'm going to go into more detail. So that's the first thing to bear in mind. The second part is about use cases and architecture. This comes from these last 2 years from us working with Rakuten as a mobile operator, but then the booming market of private networks. So the first thing, differentiator is, I put public versus private network, but it will be more non-standalone versus standalone. Non-standalone, as you know, is how I reckon we have here 5G. You have a 4G infrastructure, and then on top, you just put the radio on 5G. So normally, NSA, you don't see much Open RAN, basically because you use traditional vendors. The 4G is from a traditional vendor. As if you remember, if you want to put 5G, you have to use whatever the traditional vendor had. So you have to use the same vendor. So there is not much Open RAN on NSA, so not much virtualization in that aspect. The only way to do so is to start from scratch, like Rakuten did. They have an NSA network based on Open RAN, 4G and 5G, right? And they can interact with other vendors. I think at Rakuten, we are like 5 radio vendors. And standalone is a different story because then you have the full 5G stack, right? You have the 5G core, the radio, and then you can start having all this mix of splits. Second thing, the frequency. Frequency is important in order to take the decision of which split you're going to take. Let's start with millimeter wave. Millimeter wave has, as you know, big bandwidth, but the coverage is very small. Here we don't see a benefit to go for virtualizing a lot of the software, so split 7.2. Basically, because you're going to put a lot of burden into the transport that is not required because you don't need, for example, multi-user MIMO, something that you cannot support in millimeter wave because of the short distance of coverage you have, right? So normally going for a split 6 or even a split 2 is something that makes more sense for a millimeter wave. So what we're doing, for example, in our millimeter wave solution is that we do a split 2, meaning that we have a CU software, but then the radio and the DU goes together inside the radio, right? In sub-6, I think is the most interesting frequency because here's the one that you can mix and match the 3 different splits or even going what we call a full G0B, all-in-one G0B. That means that you put all the software inside the radio. That some use cases make sense. I will explain later on. But sub-6, I think, is the frequency that you have this mix of splits that you can decide depending on the use case. Sub-1 gigahertz is a low frequency. Normally, low frequencies means that you're going to need big antennas, right? The lower the frequency, the bigger the wavelength. So you don't have MIMO there. Normally, you're going to get like 2x2, 4x4, maybe maximum 8x8. So again, having these high-level splits is not going to give you, low-layer splits, a split 7.2, a split 6, maybe doesn't give you a big value, right? So maybe you go to a split 2 and you have a more relaxed transport. So, and then one of the last points I wanted to discuss today with you about the splits is the scale of the deployment. And this is critical when you decide which split you want to go for. Imagine a private network that is a factory, and you have like 100 indoor radios, right? These 100 indoor radios, they're going to have some interference between each other. So it's important to have this split 7.2 because you have all these coordination multi-point algorithms that really helps you to avoid interference and to get the best performance, right? Also, when you think about indoor deployments, it's quite easy to have optical fiber. So you have the solution of the transport is there. Right, so that would be a good use case for a split 7.2. But imagine now the situation of an MNO who wants to create some densification using outdoor small cells, and you have scattered radios in neighborhoods, right? You have some hotspot areas, and you put like 2-4 radios in this neighborhood, and then miles away you put another 4 or 5 radios. When you look at the different splits, you will say, well, I can go to split 7.2. I get the benefits of some of the interference cancellation algorithms. But I could go for a split 6 because, and now I'm thinking more about the economics of the deployment. You have to think that when you virtualize the radio, you're moving the software away. So that means that the radio becomes cheaper because it has less software and less hardware. Right? But now you're putting the software has to run somewhere, and they run on servers, right? Servers from Cisco, Dell, HPE. These servers, they are expensive. I mean, they have a cost. So your target as a system integrator, as an operator, is to try to aggregate as many radios as possible on these servers, because the more you aggregate, the cheaper is the whole TCO of your infrastructure. What happens when you have these scattered type of deployments? What we have seen is that it's hard, if you use a split 7.2, it's hard to aggregate many radios on the server. So instead of having, I don't know, like 30 small cells in one server, maybe you have like 4 or 5. So that means that the price of the whole solution is getting quite expensive because of the price of these servers and the small number of radios you're connecting there. So it's something you have to bear in mind as well. This is something that we have learned, for example, in the US. When you look at CBRS, cable operators are, deploying 5G networks. What we have seen with them is that they have a transport called DOCSIS that they don't want to, it's a good transport, it's not optical fiber, but they don't want to use a lot of resources. So for them, going for a split 7.2 is not a no-go because they take a lot of resources. So for them, it's better to go for split 2 or go for even a full G0B. Full G0B meaning putting all the software inside the radio. Also because of the economics, right? Because they have scattered deployments that for them will be hard to place a lot of radios in one server. So if you remember in the split 2, for example, latency had 10 milliseconds. That means that you can have kilometers away radios and aggregate them in a server. So this is an important point to take into account. This is what I was explaining. These are the different architectures, A, B, C, D. If you see architecture is the full G0B, meaning that all the software resides inside the radio. Then we have architecture B. That will be our, for example, millimeter wave. So the RU and the DU part is inside the radio, and then you have the CU somewhere else, and then you have the standard, a split 7.2 or split 6 architecture where the DU can be, depending on the transport, in the core, in the headquarters, on the edge location. So what we have learned so far as Airspan is that there is no silver bullet split, and I think it's valuable that you support different splits, depending on the frequency, depending on the use case, depending on the type of deployments, how many small cells can you aggregate, the type of transport that you have available. So what we have created is one line of software. So for our software is the same for all the radios. So we do the layer 3, 2, 1, and we support these interfaces, a split 2, a split 7.2. We're working now in the split 6 development. And what we do is, like, depending on the use case that we are seeing in the market, we provide the software in different locations, either on the radio, or we put it on the CU or in the DU, right? So basically what we are offering here at Airspan is, like, you can have the full G0B, so meaning all the software on the radio, or you can have the RU itself or an RDU, the software plus what we call the ACP, the Airspan Control Platform. That is where all the intelligence resides. That means all this plug-and-play functionality. This is something that we have seen that is very, very valuable. One of the awards, the starter kit, is related to that, plug-and-play. We are capable to mount a 5G private network in a matter of 1 day. So we bring this whole solution, and you just switch it on, and it works. So we see value in here, and the intention of this talk basically is just to clarify these pros and cons of the different splits that has been discussed today and tomorrow was mentioned as well. So that's all from my side. Thank you very much.
Thank you, Abel. That's great. Are there any questions for Abel now? Otherwise, we'll move on, and you can save your questions to the panel session at the end. That's great. Thank you, Abel. So I think at this stage we've learned a lot about the wide range of architectural options that are available, but we haven't learned very much about how to actually choose one of those to put into a specific building. I'm very much expecting we'll get more of that from this next presentation from Graham Payne from Freshwave. Graham.
Thanks, Simon. Yes, thank you, presenters, on what have been some fantastic innovations on new architecture. So I'm going to take you today on a journey towards mobile private networks. And we're going to start with a little bit about Freshwave. So Freshwave is a business. We do indoor, we do small cells, and we do DAS systems. We do masts, small cell outdoors, and masts and small cell outdoors. Over on the right, you can see we do Wi-Fi. And today's presentation, I'm going to take you on a journey to the left-hand side there on private networks. And I said specifically a journey to private networks, not towards, because we're going to share with you real-life deployments that we've done already. We do this, starting the journey down the bottom, we do this by a combined expertise of a real estate knowledge, and we combine that with real telecoms expertise. Our approach is truly collaborative. We collaborate with our suppliers, vendors, all the mobile operators, and of course, a real collaboration with customers to understand what they really need. And then we leverage global best practice. So our business is part of Digital Bridge, who are a global investor, and our sister companies like Externet have over 30,000 small cells outdoors, Boingo, huge Wi-Fi and private networks, and another example would be Digita in Finland, who delivered private networks to the gold mines in Finland. And Tom, I see Tom, he's regularly on calls with those. And interestingly, it's not just about gaining their best practice, they're picking our brains and his brain, especially on what we actually do. And I'll share that with you today. So in terms of that expertise, it starts with expertise. And these are the deployments which we've built on. On the left is small cells. We do small cells, an example is Workspace. We do 3G and 4G, deployed throughout 700,000 square feet, 18 buildings. And that uses small cells. Predominantly at the moment we use Nokia small cells, but also some CommScope product. In the middle, our expertise is huge DAS buildings. We delivered the biggest new building to go up in London, all 4 operators connected. It's a fantastic experience. I've posted on LinkedIn that the views from there are amazing. That's using solid DAS, so collaboration with solid, but of course all 4 operators, and real collaboration with 22 Bishopsgate, our customer. And then we deliver neutral host. So in the UK, the operators got together and came up with a new specification, which is a real architecture change enabling lower cost backhaul and connectivity because it connects via our data center where we put our gateways, enabling our small cells using very often shared radio nodes. We've delivered the first site. We delivered the first calls on that job specification with VMO2. And we're now in full rollout mode on that product. And we've actually got a live site, a live commercial site up and running with another operator and a pseudo arrangement with a third. So taking that neutral host is another real enabler. And what that gives us as a business is true radio and technology expertise. I started by saying how we do this is by leveraging our real estate and our technology expertise. You saw the technology expertise. Well, we've got an extensive customer base across multiple sectors. We've got over 300 live multi-operator sites now that we run. We've delivered over 2,000 connected buildings across manufacturing, real estate, enterprise. We've got public sector customers, transport customers, healthcare. We delivered the largest new hospital, all 4 operators on it to be built last year, the Grange, conference centers and stadiums. So of course, those customers tell us what they want, and on a journey to pro-mobile private networks, it's very much about what are the problems you're trying to solve. You can't force a solution on anyone, and what we're able to do is if a customer's got a problem, we will deliver the solution they need. And if that's Wi-Fi, it's Wi-Fi. If it's multi-operator service, it's multi-operator. If it's private network, we'll say a private network is ideal to solve your problem. In terms of our architecture drivers and what are the innovations that we look at and we're really building on. So one thing which hasn't been mentioned is our customers are telling us more and more, and our business is getting more and more passionate about the environment. And no one's mentioned that today yet, but I'm going to. We're looking for greener designs. We're looking for lower power. We're looking for more efficient design solutions. And the JOTS takes us one step. An enabler which would be fantastic is if the operators, the technology is available now, but if the operators got together and really used shared radios and even used shared spectrum. And I know that's a challenge, but I'm sure by collaboration and open discussion, it will quarter the power on a site and it will quarter the cost of the radios on that site. That will be a true enabler for more and more sites to take connectivity. Other enablers, and we've just announced it last week, and I'm really delighted the City of London signed off the announcement, is on outdoor small cells. We signed an agreement with City of London and Cornerstone to deliver fibre-fed small cells in the City of London. Now, when I spoke to our team about this, I said, look, if you're going to make small cells outdoors happen, you have to deliver it in the densest traffic areas where it's most difficult to put fibre. If you can solve it in the most difficult place, it will be a catalyst for the rest of the country. We know in the US, small cells have really taken off using this architecture. Our agreement allows us to do this in the City of London. Big thanks to Cornerstone, big thanks to VMO2 and the other shareholder, Vodafone, for enabling this agreement to take place. And thanks to all the operators who've collaborated on the fibre design, which over to my team there, who are now into delivery mode. So I'm looking forward to a successful trial, which will happen later this year, early next year. And then on the industry side, we really collaborate on the ecosystem, on private networks. And we've been delivering cutting-edge private networks, and more of them in a minute, where I'll share with you some real-life sites. In terms of our collaboration with vendors, we talked about Nokia. Ethernet have been fantastic. The cable-free product came in the N77 band, which was superb. We worked with Airspan, Druid, many suppliers. Because our approach is vendor agnostic and to take the best architecture to serve the needs of our customers. And what have we done? A rather complex slide, but these are our real life deployments. More on the actual sites in a minute. I'll give you 3 specific examples. But what this slide says to me is it is a complex environment, but there's a key benefit here for mobile private networks that stands out to me more than anything else, which is the bands, the spectrum. Because private networks use licensed spectrum, which gives better coverage, is more reliable than unlicensed because it's not subject to so much interference. It gives better range. So with a private network, you can reduce your radio points 10x in many deployments, which significantly reduces the cost for our customers. Where we've got environments where the Wi-Fi is unreliable, we've delivered private networks that give true reliability and excellent service. And that's because of that licensed spectrum. And the other benefit you will get from mobile private networks is much, much better mobility. So when you're moving around, especially in a fast-moving environment, mobile has a significant advantage. We've delivered 4G. Our 4G product is now in commercial rollout. We started on the 5G journey with non-standalone last year, and we've now delivered 5G standalone in local access licenses, shared access licenses in the UK, and by white labeling MNO service and delivering service for our mobile operator partners. In terms of some of our sites, it was really funny. Analysys Mason did a report yesterday. It was really well received. And I think it's luck, actually, but the 3 examples here are what they said would be the top industries in private networks: manufacturing, leisure, and transportation. The first one is our Bio-Innovation Lab. And this Bio-Innovation Lab is done for Cambridge Wireless, and it's a true industry accelerator example. It's 5G standalone. It's up in Cambridge. I was up there with Obi and his team last week. 6 companies are now actively involved. They're delivering robotics, so there was a robot connected. And we're talking to them now about not only doing that inside the building, we're talking about putting this private network outdoors to support autonomous vehicle trials in the wider area of Cambridge. Now, I won't be driving there when they're doing it, but this is the way of the world, and outdoor private networks are going to be a feature as well. The next one is a white label service we delivered for our partner mobile network operator. It's delivered in a manufacturing plant. It's over multi-sites. It's a 4G upgradable to 5G. It's using Nokia core and Nokia radios. We did the design and we did the installation, both indoors and outdoors. And a truly huge site, which is now operating on a private network with, I think I read, over 500 connected devices. And the last one I'm going to deliver, and I'm happy to answer any questions, by the way, on any of these sites, is we designed and delivered a 5G standalone network in St. Pancras Station for HS1. It's a pilot. It is using N77 band, which was difficult to get a radio product for, but Cable Free came up with that, the solution, and it was excellent. And what this does is it supports this HoloLens technology where you go down the track and you can actually do digital twin technology, and is going to really help HS1 in their maintenance regimes and their and basically minimize the costs of their operation. And they're delighted with it, as you can see from Diane Crowther there. And finally, our award-winning holiday park in the leisure sector. So we've talked about transportation, we talked about manufacturing, we talked about now the leisure sector. The leisure sector, our solution here is 4G. We don't need 5G. And the 4G is delivered because at this moment in time, the routers for 4G are lower cost. And if you can deliver multiple leisure facilities or multiple buildings on a site with a router, that component needs to be low cost. And the 5G device costs need to reduce. 5G, I'm sure, will come, but 4G is where we are now. And we're really delighted that last year we delivered to Park Dean. We secured local access licenses from the mobile operators using their 2600 megahertz spectrum. And Verdant have now taken that on, and we're into full rollout with more and more. And the big benefit for the caravan parks is when they try and do Wi-Fi to Wi-Fi, they're high interference. They've got a high interference problem. The reliability of their broadband was really poor. So if we do a 4G private network as the backhaul to Wi-Fi in the caravan, we use the licensed spectrum, which gives us better range, especially in dense wooded areas. So lots of these leisure parks are pine trees everywhere. The reliability of our radio coverage is so much better than Wi-Fi to Wi-Fi. So that's it for me. I'm happy to answer any questions.
That's great. Thank you very much, Graham. Are there any quick questions for Graham at this stage? If not, we'll move right on and pick up further questions in the panel. So the final of our presentations is, again, back to the chip architecture. Pleased to introduce Adil from EdgeQ. Adil, welcome.
All right. Thank you, Small Cell Forum, for having us here. I'm here with my colleague Sriram, who is head of systems. I head the products at EdgeQ. Am I audible without this mic? Can you hear me now? Yeah, I think it's good. Okay. So we are a small startup based out of Santa Clara, California. And we started our journey around 4 years ago when a bunch of us left our respective previous companies and wanted to do something different in the field of wireless infrastructure. We thought there's a gap in what is being provided, and we could fill the gap. We wanted to be the provider of all kinds of wireless infrastructure, not only small cells, but also macro cells as well. And we were confronted with a question very early in our journey: what is the optimal architecture, right? There are different types of use cases. I think my other panelists talked about those use cases before me. Enterprise, outdoor macro, indoor, femto cells, small cell, pico cells, all kinds of cells, right? And on the right side, you see macro base station requirement, right? For example, there is cell site deployment for macro base stations, and there are deployments for pre-aggregation nodes. And we were scratching our head on what is the optimal architecture. As a silicon provider, as a physical layer provider for 5G and 4G, we couldn't afford to flip 5 different silicons for all these requirements, right? On top of all this, there is ORAN. I think we talked all about that as well. There are different split options required for ORAN, all the way from option 0, option 2, option 6, option 7.2, X, 7.3. There's option 8 as well. And customers choose these different options based upon what are the requirements for that specific network, right? There are latency requirements, there are cost requirements, there are performance requirements. So if you add the top picture to the bottom picture, you see the complexity of how do you provide an optimal solution, right, which fits all. On top of that, there is another challenge, and that challenge is 4G to 5G transition, right? 4G is here. It's not going to go anywhere in near future. I think for next 4 or 5 years, more than 5 years, 4G is going to stay. So when a 4G band is reformed to 5G, what happens? Are the operators and the OEMs going to rip and replace the network? They are going to throw the box away, buy new chips, roll trucks to hundreds of thousands of sites to make them 5G compatible? What is going to happen, right? This is going to have a lot of cost associated with that, right, in that transition. At the same time, to meet the cost structures of small cell, 4G and 5G must run in the same box. Leave aside the box, must run on the same chip. Otherwise, the cost will go through the roof. One problem that we saw with 5G private cell deployments is that everybody, all the OEM partners and the customers, the eventual end customers told us, 5G is good. It provides low latency, high security, and high bandwidth, and all the good things. But I don't want to pay like 10x of what I'm paying for 4G. I don't want to pay 10x of what I'm paying for Wi-Fi, right? There is a break-even point, right? And we were thinking, how do we make sure that the cost of all these solutions is low? Low as comparable to a Wi-Fi cost point, okay? And Wi-Fi enterprise cost point. So this was the target that we started the journey with, to play in the field of wireless infrastructure, small cells and macro cells, solve the 4G to 5G transition problem, run 4G and 5G on the same silicon, and on top of that, I'll talk at the end of my presentation, there is an edge compute aspect to it, right? The world is changing. The world is not only about connectivity anymore. The world is about connectivity and compute at the edge. There are a lot of edge services. So one cannot say I'm a 5G modem company or a 4G modem company. You have to provide facilities so that end user applications can be run on the same chip, right? So now this was kind of the problem statement. We found the solution to these problems in the architecture that we chose, and this kind of gives you a high-level picture of what we are offering. At the base of this picture, you see a silicon. It's what we call EdgeQ base station on a chip. I'll talk more about this silicon in next few slides. After that, we offer a fully deployable physical layer. This is not a reference stack. This is not a borrowed stack from somebody. We wrote every single bit of this in this company in last 4 years. And then we are compatible to work with any layer 2, layer 3 vendor partners. I mean, some of the partners are in this room. And then we provide this solution to an ODM or OEM partner who can build a box around it and offer value-added services on top. By doing that, we basically softwarize the whole modem architecture. We could support all the splits, all the way from split 0, which is also known as all-in-one small cell, and then going all the way to the other end of the spectrum where we support split 7.2, option 6 for a macro DU deployment, right? And we basically are working with ODM partners and end customers on both of these portfolios. One is small cell. When I talk about small cell, think about femto, small cell, outdoor, indoor, everything. And the other is our product is a ORAN PCI card, which acts as a layer 1 acceleration. This is, I want to go a little bit more specific on what we are building so that you get a better idea on who we are. And many of those details on our website, so we can focus here on this slide. So on the left side, you see a cartoon diagram of the chip. On the right side, you see a bunch of building blocks. So what do we have in this base station on a chip? On the top two blocks, you see a signal processing complex and FEC acceleration. I think somebody previous to me told that FEC acceleration needs to be hard-coded. Yes, we have it hard-coded as well. Signal processing complex, we build the entire PHY on RISC-V architecture. So we took off-the-shelf RISC-V components, RISC-V cores, and we added custom instructions to it. More than 50 custom instructions were added to do all the 4G, 5G functionality. Lower layer 1 and higher layer, the entire layer 1, right? Starting from FFT, channel equalization, to channel estimation, all the massive MIMO, beamforming, weight computation, everything is done on the RISC-V processor, right? So the top two boxes here and on the right side are the what we call is physical layer of 4G and 5G, okay? Based on RISC-V, and this is all software programmable. We can program it to be a small cell. We can program it to be a macro layer 1 accelerator. Then the second subsystem is what we call a CPU subsystem. This is the second two boxes on the right side of the picture. We have a multi-core, multi-thread ARM newer CPU subsystem, a bunch of ARM cores, where we run layer 2 and layer 3 for 5G and 4G RAN. I will talk about this a little bit more in detail in subsequent slide because there are some value-added features also we have here. We have hard-coded some protocol accelerators. MAC and crypto accelerators are hard-coded to provide very low power and very low footprint for the silicon. And then there are a bunch of other necessary components like boot subsystem, RF interface. We have data converters integrated into the silicon. So we can actually connect to analog IQ interface with any RF IC off the shelf. We also have a JSD interface, which allows us to connect with any RF IC like an ADI or MaxTiners of the world as well. So we are agnostic to RF IC. We can work with any RF IC vendor. As you might have noticed rightly, for the macro deployment, the front haul becomes very fat when it comes to massive MIMO, right? If you are processing a 6040 RX massive MIMO 100 megahertz, the front haul is already like 20 gigabit per second per lane. If you're processing 3 of those, the front haul should be more than 50. We have very fat Ethernet interfaces for the front haul. We do full eSIP termination in the silicon. We have also interchip link by which the two of the silicons can actually talk to each other, thereby doubling or tripling the capacity of this whole system, right? So in the end, we get a very massively parallel, fully programmable, integrated 4G, 5G. We have AI functionality as well in the silicon built on this 5. Network processing unit and CPU is also integrated. So what you get is actually one monolithic integrated silicon which can do everything from RF interface all the way to option 0 if you need it to do option 2. Or you can also use this as a very fat, very high capacity layer 1 acceleration PCI card. Okay? So let's move on. One other problem that we saw in this ecosystem is that who does the RF and baseband interconnection and IoT testing and stuff. We took on that on ourselves as well. So we work with off-the-shelf RFIC vendors. We have few partners, and we provide what we show in this blue box. Okay, this is our deliverable to you. Means we provide seamless integration. You don't have to kind of worry about whether this RF will work with that, who does the IoT testing, whether the ACLR limits are being met, whether this interoperable with multiple UEs. We take all of that off the table for you. So our ODM and OEM partners, what they do is you take the solution from us, including the software, and you basically put RF front end and all the other components around it, and there you go. You have a solution, and then you can then you have your own value-added solution like SON and everything else, right? So we kind of become one-stop shop for software and hardware in this game, making the life of our partners much, much easier than it is today. As I mentioned in a few minutes ago, we realized that the world is going in a direction where it's not only about connectivity. One cannot say that I'm a 5G or 4G solution. If you are deploying at the edge, you have to make sure that edge services can be run on your silicon as well, right? So the ARM CPU complex that we have, we offer it to our customers so that value-added services can be run. So we offer containers, we offer virtual machines. For example, for AR/VR application, you can run a GPU host driver on the silicon. You actually can run a condensed core network here, right? You can run UPF here, or the full core network here. Once you do that, you actually have got a full network in a box, network plus RAN in a box, right? For the edge. So you can do data mining at the edge, you can do crypto at the edge. You don't have to have another silicon or software to run those value-add functions, right? So this is a truly 5G and compute platform. When I say 5G, I don't mean to say only 5G, it's 4G as well. 5G and 4G plus compute platform, right? And then the signal processing and AI complex that I mentioned before in the discussion has 5G and 4G connectivity, a bit of machine learning as well. And you get a truly polymorphic connectivity and compute on EdgeQ RISC-V processors. And the applications are running on the integrated host CPU here, right? So I hope you appreciate the level of integration that I'm talking here, right? It's a true solution for edge compute, including 4G and 5G. You can run your own applications on this silicon as well. Remember in the beginning of the talk, I talked about the problem of 4G to 5G transition, right? What happens when an operator reforms a band from 4G to 5G? Do you throw away the box, or do you buy new chips, or what do you do, right? Because this is imminent. 4G to 5G transition is happening in the next 4 to 5 years. Many of the 4G bands will transition to 5G. So this is the solution that we offer to our customers. Let's say that you are running this silicon, and you have basically a solution where you are running 5G plus 4G, dual rack solution. Let's also assume that 5G is a 4x4 N78 band, and let's assume that 4G is band X. It's actually built for a particular customer. I'm not allowed to say who is, so I use the word band X. What happens when this band X is transitioned to band NX, an R band, for same bandwidth, right? Because the physical layer of this chip and the entire chip is so malleable, this is how the solution looks like. This is the same RFIC, same HQ SoC. We give you a software upgrade, and boom, you are doing 5G dual band G Node B. 4G has been transitioned to 5G. There is no box changing. There is no hardware changes. There is nothing there. We give you a software upgrade, and you are done, right? This is something that is resonating with a lot of our customers, and actually, we were asked to provide this solution many, many years ago because there were a lot of people on our board, which I'll show, who kind of foresaw this coming, right? So we architected the chip having this in mind. Once you do all that, then you got a solution which can scale across many different types of solutions, right? It can scale from femtocell to enterprise to outdoor to macro, depending upon the split you choose for the different KPIs that these boxes are going to hit in terms of latency, in terms of power, in terms of cost. For example, femtocell is very, very cost-sensitive environment, right? It is low-capacity femtocell. And on the right, this is still, we call it small cell because the number of users are very small. But this box on the right is transmitting 40 dBm EIRP per port. So it is kind of not a very typical low-power small cell. It is low-power to high-power small cell, right? So what you get is this solution, which is very malleable, very flexible. All these boxes have the silicon, HQ silicon inside and the software inside. And these solutions can be provided at enterprise Wi-Fi economic cost points because there's massive integration going into here, right? Last but not the least, this is a team which made it work. There are a couple of us here. We are privileged to have very, very luminous advisors who kind of guided us from the beginning, who foresaw what is required for wireless infrastructure. And we have a very distinguished team coming from who's and who of the industry. I believe that's it from me. Thank you very much.
So I'm going to assume that if you have any questions directly for Adil, you'll ask them in the panel session. I'd like at this stage to invite all of our speakers to join me on the stage. Also Peter Claydon from Picocom.
I'll get some water for myself.
Absolutely. So while the architecture Avengers assemble here, we've covered an incredibly broad range of topics between those questions. And it will be quite difficult to find questions that fit with every one of the speakers. But I'm going to start by posing a fairly general question, which I'll invite all of the panelists to take a stab at, starting with Peter, since you haven't had a chance to speak yet. And then I'll go on. I have some specific questions for each of the panelists in the different areas. But please raise your hands at any stage if you'd like to ask a question. We have a good 30 minutes or thereabouts for the panel, so there's plenty of scope for you to dig into some of those issues as they came. So panelists, it's great to see this huge range of architectures, and positively that means we have more choices to tailor solutions for particular environments, whether it's in or out of building, whether it's coverage or capacity driven, and so on. But that also brings with it a few challenges. It brings challenges for folks as product people to figure out, do I need variants of products to cover all those permutations and combinations? It brings challenges for chip designers to meet those different requirements, and it brings challenges for those deploying to actually have solutions that are kind of approved by the set of operators that you're deploying for, but are also efficient in those environments. And there's one other layer of challenges that brings, where we're thinking from a sort of national and supply chain security perspective, that we need to sort of help to enable this kind of open ecosystem so that there are choices of vendors, and that brings innovation and resilience into the network. But we're still at quite an early stage, truth be told, with those open interfaces. And having many splits and many options actually risks fragmenting that market just as it stutters into life and scale. So that's, you know, the broad question is, how do you get that balance? Where do you see the challenges? Do you see needs for actually the industry to come together around more consolidated architectural options, or is it vive la différence and you love that you know, wide set of choices? Peter?
Very good question. I mean, and it's a very broad question as well. I think, you know, there are other dimensions to this as well, which are, we talk about split 7.2, but, you know, even in the small cell world, what frequency band are you in? You know, we have customers doing, you know, 2T, 2R, 4T, 4R, different power levels. You know, is it a 24 dBm indoor small cell, could be 27, could be 30, 33. There are all these combinations. I think what we're seeing is there are certain areas in the small cell world where this does make sense. I think the kind of indoor band N77, you know, kind of say 24 dBm, 4x4 MIMO. That's one area where I think we are seeing the possibility of interoperability, and you know, people doing deployments can go and pick things. I mean, there is also flexibility within the small cell itself. I mean, I think we covered things like, you know, we could cover a 200 megahertz bandwidth with 4T4R and put whatever you like, any combination of things within that. So I think you have that interoperability, that capability, but even then you actually have to test this. So there's a big challenge there. But you know, so more generally, I think that these things are quite complicated. And when you start looking at macrocell, I think this is why our friends from BT are sort of saying that, you know, when we see Open RAN in the macrocell, I think they said 2028 potentially. We're talking about going, you know, certainly moving on to 6G there.
So what sort of practical steps would help, Peter? I mean, I believe you've been sort of active with others in Small Cell Forum on, for example, a sort of standardized product specification to help with that.
And that helps, and I think the standardized product specification, it comes up very much along those lines. You can, we did look with Ikana at, you know, flexible front ends, like a front end you could change out. I mean, that's a good idea, but I mean, in practice, it's quite easy to spin a board. So you probably end up with, you know, if someone wants different frequency bands, they'll end up having a single board there as well. But it's helpful to have the interfaces well defined. In that case, you know, between between the radio transceiver and the RF front end,
right,
in particular.
Yeah. So same general question for everybody. I'll start along here. You know, are you thriving on that wide range of architectures and want more, or are you seeking some sort of industry clarity around maybe a subset of architectures to align around?
So I guess the answer might be a little bit, I would say, easier for an SoC provider, because from our perspective, essentially we have to enable the solutions, and we have to have a very clearly specified set of functions that need to be accelerated. And then we have to offer solutions that cover the range in terms of number of antennas, then the ports, and also power consumption, reduce it as much as possible. So we are essentially trying to go for the optimal power, size, and basically weight product that then you can sort of modularize and either use it as a small cell in some cases, and in some other cases you can put it in a card and then allow the customer to have as many cards as possible. Mm-hmm. So with a pooling solution, then, for instance, on the DU side, then you can scale up to whatever customer needs you have. On the small cell side, like you have a 2x4, 4x4 solutions. Again, it's the focus is on talk about standards, making sure that the standards want to integrate with the higher layer solution that ultimately ends up in the end product that the operator sees. That interface has to be capable. So you have to make sure to support all the MU-MIMO combinations, all the massive MIMO combinations, MTRP combinations. So we have to make sure to keep that standard abreast of where the market is to be. So essentially provide a range, minimize power, maximize performance, minimize weight and size, and then that makes it easier to meet the customer where they need to be.
So Abel, it sounds like chip companies like Qualcomm are giving you a lot of options, but you've still got to turn that into a specific product roadmap with a finite set of products.
Correct, yes. I would say that we are in the learning curve by experience. That was, what I presented was, these last 2 years being with Rakuten as a first Open RAN mobile operator, but then the success of private networks, we are more of, I think we are in 70 private networks, 5G right now. So what we're trying to do is to be laser focused of what works and what doesn't work. So we're very much in touch with the market and also with all the partners. We are big partners of Qualcomm. So of course their technology help us to evolve faster and bring products into the field. But what we have learned is this flexibility, right? You have all these splits and you have to understand, and you have to also to explain to the customer, I think Raham was mentioning that as well, what is the solution from our experience that fits better the use case, depending on the situation they have, the type of deployment, the type of transport, for example, the type of features. So knowing that, what we're creating right now is like, you can call it blueprints. I know that there's a bit of, people are scared when you hear blueprints. You go, oh, you're going to create a silo there. I don't think that's the issue here. For example, we created we can call it a blueprint for Rakuten, but we are talking about 5 radio vendors, right? At the end, if we go to another MNO, that they have another 5 radio vendors. After you have like 3 or 4 blueprints iterations, everyone has an integration with each other, right? The same is happening with private networks. We partner with many partners like Druid, for example, the core network, but also on devices, Qualcomm. So what we see is like, what does it fit for specific use cases? The US CBRS is a type of use case. We have the UK with the 3.8, 4.2 share access. So we partner with different industries, and we create this flexible solution of supporting different splits, moving the software in the radio, outside the radio, and we see what it works, right? Because at the end, as it has been mentioned here from the analysts, there are certain verticals that are pushing the 5G, right? Like factories, for example. So we have specific solutions that we know that work right now. And the idea here is like to extend these blueprints. At the end, I believe in a few years, we will have like this hopefully this multi-integration, multi-vendor solution. So that's our perspective, how we work.
Fantastic, thanks. Graham, I get the impression you discussed a number of different architectures that you use. I get the impression actually the limiting factor for you might not be the availability of architectures, but actually getting operator acceptance to share in one of those architectures.
Yeah, it's a key component when you're delivering the multi-operator buildings we deliver, is getting the operators in line with that technology. And so what we do is we just work with them and collaborate with them indoor and outdoor, and are led by them, to be honest with you, on the product. So if one operator wants to do Nokia, another Ericsson, another ORAN, then we will work with them, and we'll just enable that to happen. So our guys are experts at delivering any of those technologies. And what that means is where we probably pioneer. So we pioneer and we go first to market. We're first to do the centralized service node with Spider Cloud, first to do a call on neutral host, first to do all 4 operators on small cells. And we're out there doing the first 5G standalone. So being first gives us that first mover advantage. In terms of the ORAN and the CRAN world, one thing we discuss a lot inside our business is as these products move into mobile private networks and being more important to customers, these customers, it's a critical service for them. If that site goes down, their business stops. And one of my concerns on ORAN and CRAN is as the products are developed and it's very complex, if that means it's unreliable or it's up and down like a yo-yo, it's not going to work for the industry. So, in all these architectures, complexity can lead to, bugs and things like that. So I'm a little bit concerned that the products coming they have to be more reliable than they've ever been before. Because getting access up there to something that's up and down like a yo-yo, when they want it fixed in 30 minutes, and it's going to take us 2 days to arrange a cherry picker to get up there, it's not going to work.
Not going to happen. Yeah, that's well said. So Adil, you made quite a feature in your presentation of having spanned a very wide range of use cases and looking to do that with a very consistent chip footprint. But there must surely be trade-offs for you, at least across that performance opportunities and hits in different environments. So how do you really reconcile that wide range there?
Yeah, so let me take a step back and maybe discuss why these different standards and why these different options exist, right? Open RAN was born because operators felt the need to disaggregate RAN because they thought they are logged into one particular vendor. They saw that if there is a better layer 1 physical layers available, if there is a better layer 2 available, they cannot do anything. They have to buy the box from one vendor or two vendors, right? Different types of options exist because they feed particular needs of the market, right? There are low latency applications, there are low power applications, there are low cost applications, there are all kinds of different applications. So the name of the game is being flexible to be able to operate in as many markets as possible. And that's what I think is the key challenge and also an opportunity, right? What we did at EdgeQ is we believe that we kind of struck a balance, went with RISC-V because we could break the barrier between softwarization and power consumption. Tribal knowledge tells you that if you tell somebody that I'm softwarizing something, the first reaction will be, oh, you must be consuming a lot of power, right? You have to break that connection between softwarization and power consumption. And then at the same time, you have to make sure that the resources are malleable such that with these different use cases, you can reuse the resource. There's no dead silicon anywhere left. You can reuse the resource if you move from one use case to the other.
Mm-hmm. Thank you. So I'm going to move to some slightly more specific questions. Perhaps for those to my right here, both of you, I'm thinking about the sort of multi-box architecture of small cell solutions inside. And Qualcomm's been very active in the creation of FAPI, for example, and arguably FAPI and MFAPI are perhaps some of the most interoperable interfaces within the RAN, and certainly some of the more mature open interfaces, and that creates an opportunity for an architecture with multiple splits in it. But the choice of that 2-box versus 3-box architecture, where's the dividing line? I mean, you mentioned, for example, interestingly, Abel, that when you think millimeter wave, you might even be thinking as split 2 scenario. But I can't imagine that millimeter wave is going to be deployed on its own in these environments. So haven't you got then a tension between the sub-6 gigahertz bands and the architectures that might suit them versus what will come from millimeter wave? And I mean, I realize we're at a very early stage with that.
Okay, so Gordon, I can start first. When you see this combination of frequency, first of all, it's good to have multi-frequencies because they don't interfere each other, right? So then you need very low-level splits. Low-level splits normally, you start working with the PHY, with the physical layer. When you start working with the physical layer, you can avoid interference. I mean, interference is the same frequency. When you have different frequencies, the important thing is to have an anchor, right? Meaning that you have normally it's the layer 3, that is the CU. So that's why a split 2, you can do, for example, millimeter wave with a split 2 and then use a split 7.2 on the macros, for example. So again, I think that the understanding of the overall benefits of the splits really led you to combine how is the best approach to deploy your network. That would be basically for an MNO, could be also for private networks. Private networks, they have a lot of interest of deploying millimeter wave. At the moment, it's not possible because end devices don't support standalone millimeter wave, and 5G private networks that are normally standalone. So this multi-box concept, what we are trying to do is like the software is the same, right? So we have their own, all the splits. As I mentioned, we do split 2, full G0B, split 7.2. We are developing the split 6. But all of them are going to be always in our solution. So again, the way is like how you move parts of the compute of the radio, and you remove them and you just let them run on the server. So this create, and I was mentioning this Lego similarity that the radio at the end you say, okay, so this part of the software goes here because I can get so many new features and I have this type of transport. So this is what we're working on at the moment. The radios that we do, we can do full G.B, split 2, reuse it. We will see if we can do a split 7.2, split 6, same radio, and see the pros and cons of having one unit that can do both splits at the same time. So we're working on that one as well.
Okay, great. Andrei, any further thoughts on the impact that FAPI and NFAPI have had?
So specific with respect to this multi-box solution, right? If we're talking about like a sub-6 solution, the impact in terms of where the heavy compute is going to be different than if we're talking about a millimeter wave solution. So if a massive MIMO type of solution, for instance, is going to require a lot of DU power. So you want to make sure that the DU is really separated and you can scale it separately. Whereas if we're talking about a millimeter wave solution, okay, the need for massive spatial compute is not, it's not there because the compute basically has been pre-baked into the millimeter wave solution, and you do the appropriate sort of beamforming towards the end user. So effectively, that's actually a very good situation where this scalability that is offered of making sure that you hyperscale the right solution and don't sort of just offer a single solution to fit all cases. That's basically, that's where sort of FAPI gives you the interface, but the scalability ultimately has to be in the architecture. So since you raised the point of FAPI has to be able to accommodate all these sort of front-end interfaces for millimeter wave or sub-6, even for small cells or for FDD, TDD, all of those have to be possible. Once those are possible, scalability is a solution. And then to go back a little bit to your question is, how do you make sure that you have you address the customer needs? You don't, you obviously you have to the SoC support FAPI, but in addition, you create templates that are of interest to the industry. So for instance, we have an enterprise template, a private network template for factory, for instance, that we worked out with Microsoft Azure, and then this way we offer basically the appropriate dimensioning that the customer needs, so they can figure out how many points they need, how many small cells, for instance, they might need. So it's not fully turnkey, but it is close enough. Maybe they need to add a hood, paint it a little bit better. But again, templates, scalability, standardized interfaces, those are really the three solutions that are needed.
That's a great recipe. Thank you. Thank you. So I'm going to change gears a little bit and turn to those to my left. But I'm on the lookout for hands. If anybody has questions, please don't be shy. Go ahead and raise them. This is, after all, a small cell event, and I'm interested in probing a bit the sort of upper limits of small cells and the environments that they can serve. Now, multi-operator environments, Graham, were always seen as something of an Achilles heel, really, for the applicability of small cells, because basically you needed a small cell per operator. That hasn't actually stopped you from pressing on and deploying multi-operator solutions with small cells, but you also made a call for opportunities for more sharing of the active equipment and even of the spectrum. So could you talk a little bit about what are the barriers to that, and what would it open it up if it was possible?
Yeah, so the current solution is we put 4 boxes up, one per operator. And obviously that's 4 radios, 4 times power, 4 times spectrum, 4 times the cost of the solution. The JOTS neutral host allows us to put our own gateway in our data center, share the front haul cost, which is a significant saver, and then it allows us to put a common radio. And so there are products in the CommScope product we use, but there are other products available where it's actually got 4 radios in the one housing. It's still 4 radios. And it's still taking 4 times the power, and it's still costing 4 times as much. Maybe not 4 times as much, but the optimal solution, so if you look in an environment like this, where you've got a conference, even in an environment like this, one radio would support the capacity needs on 4G.
Interesting.
And in an enterprise environment, one radio would definitely support. So in our offices with people on PCs and laptops and so on, one radio would support all the capacity we need.
Fantastic.
And so if the operators were to collaborate on the neutral host design, enabled by that architecture, it would allow one radio, one frequency, and it would core to the power, a much, much greener solution, and a much, much lower cost solution. It would be a real enabler for not just we do hundreds of multi-operator small cells, it would be an enabler for thousands.
Well, that's a really compelling opportunity, but if you sort of work out what that means in terms of products, sort of in the limit, you might have 4 operators wanting to make use of all of their spectrum across, 3.4 to 3.8 gigahertz, and then a bunch of private needs sitting up in 3.8 to 4.2. So chip designers, we needed a chip that goes into one of a single radio and associated DU for Graham that spans the entirety of the capacity needs of 3.4 to 4.2 gigahertz and do it with less power than we have today. How do you feel about that challenge?
We can help you, yes. We do have a solution. In fact, going back, when we were starting the design of our PC802 chip, we saw this was one of the challenges, and we can, depending on how many antennas you've got, we can cover 200 or 400 megahertz of bandwidth from one piece of silicon. And again, depending on radio transceivers, analog devices that we have on our reference board, that covers a 200 megahertz bandwidth, and they're becoming available to cover 400 megahertz. So you can do this all within, it will be one piece of silicon, and you can put within that sort of, say, 200 megahertz of instantaneous bandwidth, you could actually use any combination of parts of it. Whether or not, the operators kind of like that or not, I think it's a sell, but it certainly gives them the lower cost, the lower power dissipation. I mean, of course, the other thing is in shared access spectrum, the UK shared spectrum and 3.8 to 4.2, for example. I mean, you can do what I would refer to as a dense air style of neutral host, where you're just broadcasting the PLMRDs for various operators in that shared spectrum. You can do it in CBRS as well. And that's another possibility. You just take a couple of hundred megahertz of that spectrum, and you can flexibly use that. And that's, I mean, I would say that's quite a likely way people are going to go.
Yeah, fantastic. Adil, can you rise to Graham's challenge there?
Absolutely. I mean, look, what we think is, we think of a modem as a computer, right? It is actually should act as a computer. What we are talking about, multi-user, multi-operator environment, this has been done not in the operator world, but in the server world for last decades, isn't it? Right? We have a server which can do anything. I mean, you can run 20,000 different applications and it just runs it, right? Why modem needs to be so different? I understand the RF challenge. I mean, if you change the band, you have to change the RF. But the modem has to be stateless. It should act as a computer. I'll expand the question. I mean, not only multi-operator, right? It should be multi-use case as well. Same modem, you are running URLC use case or you are running EMBB use case. It shouldn't act differently. You should be able to slice and dice the modem and be able to run anything that you want. It should simply act as a compute entity. I think this voodoo and this tribal knowledge about modem being different, I think it has to be challenged now.
Interesting.
It cannot be that, oh, this is modem, this must act like that. It won't work. The modem should be a compute element, should be able to process anything and everything that is fed to it.
Interesting, yeah. Just to revert back to you, Graham, as a sort of consequence of that, these gentlemen seem to think they could rise to that challenge.
I'm convinced the product is there. It's already there. The wider bandwidths will make it even more compelling. And the key barrier is it's a collaboration with the mobile operators who are then giving more control over the network and the quality of the service to their customers. So what you need to really do is make sure the operators remain in full control of their network, their customer experience, at all the deployments, and it's got to be a collaborative, trusting environment which serves all 4 operators equally.
Makes sense. I mean, I know you reach in the toolkit for the DAS when we're in the really large-scale multi-operator environments. If, however, you had acceptance of the kind of products we're talking about there, does that nibble at the heels of the DAS?
In the large sites, I don't think so. I mean, the huge sites, a DAS is still a cost-effective solution. We'd like the operators not to deploy a 60-watt macro base station, right, which we attenuate down and waste all the power. We'd like a low-power base station.
Not entirely green, is it?
It's not entirely green, so that's an ask we're discussing with them. But the larger sites, the DAS, it's still one radio, and it's across the various bands. So the 22 Bishopsgates, the Scalpers, these sort of things, there's still a place for the DAS in this world. The middle market, hotels, conference centres, enterprise buildings, office blocks, they're the environment which would really benefit from a one radio serving all operators.
Right. And then just to stretch the small cell boundary even further, and interested in thoughts from any of the panel on this one, Doug actually mentioned distributed MIMO. And a very, very long time ago, 1996, I had a PhD student working on, we didn't call it MIMO then, but it was distributed MIMO in an in-building environment. We didn't remotely need the levels of capacity that were required for that, but it was an interesting idea. So, and what we're talking about here could also be seen as coordinated multipoint, which I think you mentioned as well, Abel, where you actively, jointly process signals across multiple radio points. And in the limit, if you get that right, there's no such thing as interference anymore. There's no such thing as sectorization anymore. You just have sort of flexible bubbles of capacity and coverage following your users around. Doug's chortling mightily over there now. So it's been intriguing for me, both in the macro and the in-building environment, why there's been very little actual practical activity and deployment of comp. Is it because actually we don't need the capacity density, in which case, when do we? Or is it because it's too hard to make it work nicely across any realistic distribution? But in-building should be perfect because you have dedicated fiber and interconnect in that environment. So when are we going to see these distributed MIMO systems?
I can go first. That's a great question. Actually, I think we're working on that. That's good news. Mm-hmm. There is this Oran Alliance feature called Front-Haul Multiplexer. Basically, what it tries to do is to combine several small cells working as one, and that's very interesting in order to compete against the distributed antenna systems. Is a great solution when you have these big venues. The problem with that, of course, the price. If there's a big venue, it makes sense. Basically, not so much about the macro you have to put, it's about the infrastructure. You have to use like a specific type of transport, CPRI, which is quite expensive. When you move to small cells, imagine an Oran Alliance split 7.2, you can use optical fiber, for example, that is cheaper, and maybe you have it already in your building. And the idea here is that you can offer more capacity. When you think about that, normally you have one macro station that is feeding all the access points. When you have a small cell, one small cell is using, it's half a small coverage and it has all the spectrum. The thing here is that, as you were saying, you don't need so much capacity. You don't have to have, 100 or 1,000 small cells, each individually having fully capacity. What happens if you can combine, instead of having 1,000 small cells, you can combine them in groups of 100, right? So you're creating areas with 100 small cells that are seen as just one radio. And also that helps you in the scalability, because now the DU, the server that we use to connect all these radios, they don't see 1,000 radios. They see only like 10 groups of 100 radios. So you can improve the scalability on the DU. So you create a cheaper ecosystem. So I think it's something that is coming. We are working on that actively. Oran Alliance is finalizing this feature, but I think it's going to be something that is going to compete a lot against the DAS. So,
really interesting.
So all these features brings these new architectures that bring, at the end, benefits for the end customer, because it's going to be cheaper deployments.
Thanks. So it might come. Mm-hmm. Any other thoughts on that?
My learned colleague, Martin DeSeco, was speaking in a session after this. His theory is why comp hasn't taken off, and it's been around since a long time, was that thanks to Qualcomm, as handsets got a lot better and able to kind of throw a null in the direction of some interference from enabling cell. So this is something that kind of became unnecessary through improved handset technology. But I mean, distributed massive MIMO, I know Huawei's said a lot about this and what great performance they have improved, and it certainly does. I don't it's something you can do. I don't know. Graham saying, do you need to do it? That's another thing. If you're using split 7.2, you can basically take resource blocks from a UE from several different access points and combine them together flexibly to create that distributed massive MIMO.
Fantastic. It's coming. It's coming.
It's coming.
Excellent. Exciting. Well, I'm getting signals that we might be getting towards the end of our time, but let me just leave a little pregnant pause to see if there are any burning questions that people have been holding on to there. Fantastic. If you could give your name and organization.
Thank you. My name is Michio Kashio from Japan, focusing on 6G. So I'm a bit off of what's going on in 5G. So I have one question for Qualcomm and one question for Airspan based on your presentation. For Qualcomm, you explained about the division of DU and CU based on 3GPP and also based on what else? ORAM alliance. And if company A choose 3GPP division, and if company operator B chooses ORAN alliance division, does the network still work as a one serial network, or do they have to agree to choose one? That is my question for Qualcomm. And my question for Airspan is, when you compared traditional network and advanced network, you put DU in edge section, and please allow me if I'm mixed up with multi-access edge computing with DU alignment. Does this DU under the edge box mean, is it equivalent or identical to MEC system? So that's my question for.
There's a couple of challenging architectural questions for you. So I think the first one was around compatibility if different interfaces are chosen. These are basically alternative paths, right? You can't mix and match in one architecture.
So I mean, there's no fundamental incompatibility, right? Once you use a split, you have to go with a particular interface that has been defined either in 3GPP for the split 2, or in ORAN if it's 7.2, or in 6, it's going to be kind of FAPI type interface. So you can mix those interfaces. Obviously, you can't sort of pair up an SR you would expect to option 6 with an DU that is going to output option 7.2. But as long as the two endpoints understand the same interface, the interfaces are very clearly defined, and in fact, the openness is the key. And openness is essentially what allows all this mix and matching. You can even have different splits in the same operator, right? You can have an operator that will choose like a 3-box type architecture for a wide area network, having kind of both split 2 and split 7.2, and then you might have in the same network maybe that same operator also serving a private enterprise where they might choose split 1 or split 2, and as long as again it's in different areas of the network, it works. You won't be able to mix splits in the same chain.
Thanks, that's great. Now the second question, I'm not sure if I got it exactly, but I think it was around the distribution of like edge compute alongside RAM functionality to the boxes at the edge of the network.
Okay. So the reason of distributing the software, so putting away from the radio, there are several benefits. One is the features, right? You need to have the software disaggregated from the radio if you want to control many radios, right? There was the reason about the coordination multipoint. Why coordination multipoint didn't fly? Because there was no much centralized software, like disaggregated software. You know to know what the radios are doing in order to collect this information. That's why, again, all this Open RAN, Split 7.2, I think is going to enable coordination multipoint. So that's one of the benefits, having more features and enable. For example, related to the EU, when you look at carrier aggregation in traditional macros, you only do carrier aggregation on the same site. You cannot do inter-site carrier aggregation. So two macros that they're covering in the same area, they cannot carrier aggregate because there is no communication between both. You know, each of them have the software on the site. So that's why all this disaggregation bring better performance. The second is to create this flexibility of the deployment, right? The features of low latency. You can move parts of the software, the user plane, closer to the edge, but also the core network. For example, we do that with Druid, the UPF, the part of the data can go to the edge. So then you can reduce the latencies there as well. So again, more performance. And finally, open up the ecosystem of where to place the software, right? You can put it in now in IT servers, but you can put it in the cloud, right? Hyperscalers are becoming like a big player also for this type of network. So many benefits there as well.
Splendid. Well, we unfortunately do have to wrap up. I could have kept asking questions all morning and beyond, I think, and we've learned an awful lot about the really rich range of architectural options that are opening up for us and lots of fuel for future events. We've had a fantastic range of panelists. Please join me in thanking them for sharing their expertise with us.